The main target of this project was to design a chemical plant that produces 99.5% purity bioethanol in a volume of 30,000 tons per year. Problem statement. Why was bioethanol picked? Because it's an efficient fuel additive with less harm on the environment than its alternatives. It is produced by the alcoholic fermentation of glucose obtained from sugarcane using catalysts. A chemical plant yielding 30,000 tons per year of 99.5% purity bioethanol from sugarcane is the main goal of this research project. Project and design objectives. Research was conducted on different processes and designs in order to achieve that 99.5% purity bioethanol. Design a plant that achieves 99.5% pure bioethanol from sugarcane. Design a process specific to the UAE and GCC regulations and conditions. Reduce the efficiency of the cost rate of fuel by up to 5% by selling bioethanol to be blended with gasoline. Reducing the carbon footprint of fuel production was also one of the main goals. Some of the applications of bioethanol include blending with gasoline, which is the main and most popular focus. It can be used as an octane enhancer. Elevated octane number is an excellent method of enhancing engine performance by reducing knocking. It is more eco-friendly than its alternatives because of the less emissions than fossil fuels. Its industrial and chemical uses of 99.5% alcohol is needed for the pharmaceutical industry. Feedstock selection and plant location. Why was sugarcane selected? Because it has a high concentration of readily fermentable sugars. It has year-round availability through global trade routes. And because of its proven feedstock for high-quality ethanol yields. Also, the supply chain advantage was one of the main reasons. It is imported from India and nearby regions like Vietnam and Egypt. There already are established routes between the UAE and India for sugarcane trade. That makes it more cost-effective in transportation and availability than its alternatives. The plant location chosen was in Al Ruwais, UAE. This was due to the close proximity of the industrial infrastructure, access to water treatment facilities, and its strategical location being 2.5 kilometers away from residential areas, which makes it a good safety compliance. The coastal location also supports utility access and logistics. Literature review and technical background. There were three main steps in the production of ethanol using sugarcane. One is the pretreatment phase, where sugar extraction from sugarcane is conducted. In stage 2, conversion of sugars to ethanol using yeast takes place. In the third and last stage, removal of water to achieve fuel-grade ethanol is conducted. Some of the other common feedstocks are molasses and biomass like bagasse and straw. However, sugarcane is the more feasible option, as explained before. Some of the key challenges faced throughout this research project was the ethanol water system forming an azeotrope at 78.2 Celsius. Another was limited separation using simple distillation. The industry insight: fuel ethanol is in very high demand in the US and Brazil, more than other areas. However, there is an increasing global interest in renewable fuels, and the UAE is already building its first bioethanol production facility.
This slide shows the raw material and how the process works. Sugarcane is main raw material. It contains sugar that we converted to ethanol. Water is used for extraction and processing. Yeast help convert sugar into ethanol. Lime and SO2 used to remove the impurities. The process runs continuously in a steady state. No mass loss. What goes in is equal what goes out. Fixed efficiency. Our goal is to get the high ethanol yield with low energy and safe operation. For the process alternative, we sell another process option. It uses milling, fermentation, and MTBE. Here the problem is we found that it is lower sugar extraction. Sugar losses is in the waste. MTBE is unsafe for the environment and safety concern. Possible ethanol losses. So this option was not the best. In the process selection, we compared two processes. The diffuser gave us the higher yield in 92%. Both same selectivity, membrane safer than MTBE. So we selected the diffuser plus membrane because it is more efficient and safer. For the BFD, this is the process flow. Sugar is extracted from the sugar cane in the diffuser. Juice is cleaned by the reactor and clarifier. Fermentation from sugar to the ethanol. Separation, we separate the ethanol from the water and from the others. So the final product is 99.5% purities of ethanol. The process is designed to maximize the ethanol production.
This slide presents the process flow diagram, which shows the complete industrial pathway for producing bioethanol from sugarcane. The process begins with raw sugarcane entering the diffuser, where fermentable sugars are extracted using water. The juice is then treated and clarified to remove suspended solids and impurities. After clarification, the clean sugar solution is sent to the fermentation section, where sugars are biologically converted into ethanol. The fermented broth then moves into downstream separation units, including a centrifuge, distillation column, and membrane separator, to obtain the final fuel grade ethanol product at 99.5% purity. For clarity, the highlighted equipment shown in the legend represents the most critical units in the process: the diffuser, fermenter, distillation column, and membrane separator. One of the most important units in the plant is reactor 2, which is the main fermentation reactor. In this unit, sucrose is converted into ethanol and carbon dioxide using the microorganism Saccharomyces cerevisiae. For plant-wide design calculations, this reactor was modeled on a continuous stirred tank reactor basis to determine the required feed and output flow rates needed to achieve the annual production target. The reactor operates at approximately 30 degrees Celsius with a residence time of around 14 hours, allowing efficient biological conversion. Based on the design assumptions, the reactor achieves approximately 92% of the theoretical ethanol yield. In addition, yeast recycling is incorporated to improve productivity and reduce fresh catalyst consumption. After fermentation, the ethanol-rich broth is sent to the purification section. The first step is distillation, where ethanol is separated from water and other remaining components. This unit increases ethanol purity to approximately 95%, but it is also the most energy-intensive unit in the process. However, due to the ethanol-water azeotrope, conventional distillation alone cannot achieve fuel-grade purity. To overcome this limitation, the distillate is sent to a membrane dehydration unit. The membrane selectivity removes residual water, allowing the final product to reach 99.5% purity. This approach was selected because it is more energy efficient than relying entirely on distillation, avoids hazardous entrainers such as MTBE, and improves overall process sustainability.
Material balance. So let's talk numbers. The technical integrity of our plant is anchored in a precise material balance. So we process around 50,000 kg per hour of sugarcane. While the feedstock is primarily water, our design is optimized to extract every single gram of value from the 13% sucrose content. So by implementing a diffuser system, we achieve 98% sugar extraction efficiency, which is far surpassing the traditional milling. And we combine it with a 92% of fermentation yield and a 99% of yeast recovery. So we don't just meet our targets here. So we guarantee a steady state output of 30,000 tons per year of high purity bioethanol. This is industrial scale engineering backed by mass balance validation. Now moving on to the energy integration. Efficiency is not just about yield, it's about energy, and energy costs money. So our process requires roughly around 2,100 kilowatts for heating and distillation. And to make this sustainable, we have come up with a circular energy loop. So instead of relying on external utilities, we harvest the bagasse, the fibrous byproduct, and repurpose it as our primary fuel source. So by integrating this recovered heat directly back to the diffuser and the reaction stages, we have cut down on operation costs and significantly lowering the plant's carbon footprint. Yes, you heard it right. We'll be using sugarcane to process sugarcane. So we are essentially using the waste of sugarcane to power the production of fuel. In conclusion, we have delivered a high efficiency solution pathway tailored for the UAE and the GCC infrastructure. By selecting the diffuser and membrane dehydration pathway, our plan stands on three pillars: superior efficiency, energy circularity, and strategic value, which is enhancing fuel performance and supporting the UAE's green energy transition. So we have not only just designed a plan, We have designed a future-ready contribution to the UAE's industrial vision.